Welcome to Tracking Through Containers and Occluders in the Wild. My name is Basile Van Hoorick. In our dynamic world, occlusion and containment happens all the time, which significantly complicates learning comprehensive scene understanding abilities for AI in many practical applications. Therefore, we introduce a new method for visual tracking of objects with persistence, including the segmentation of any surrounding occluder or container that might be in the way. For example, the orange fish in this video who is responsible for hiding the yellow fish. Concretely, our network predicts 3 masks for each frame. One to localize the target instance we want to track, a second one to mark the occluder in front if one exists, and a third one to mark the container around it if one exists. Here's one more example. Given a query mask for the toy duck in the first frame, we drop it inside a container, which implies that all the appearance features of the object have completely vanished for a moment. However, our model recovers the containment and later re-identifies the same duck, suggesting that it is capable of advanced spatial-temporal reasoning and correspondence over time. Both our dataset and our model are called TCOW or TCOW. For context, video object segmentation is a well-known task that involves the fine-grained separation of foreground objects from the background in videos. However, it typically does not consider a notion of object permanence, which means that things continue to exist even when they are no longer visible, and is necessary for a true understanding of complex dynamic scenes. On the other hand, ground truth information for fully occluded objects is difficult to obtain, because often there is not a single right answer in the first place, due to the aleatoric uncertainty about the situation. Our key idea is to modify the task and rephrase the question to become who is the responsible occluder, rather than what is the precise location of the hidden object. This way, the problem of inherent ambiguity is dealt with in a more principled fashion. Similarly, we can also ask the model to predict which container is responsible for encompassing the target object. Of course, one and the same object can create both occlusion and containment at once too, as in this example figure, and in the visualization, combining red and blue gives us a magenta mask. Annotations are extracted from synthetic data, specifically the Kubrick simulator, where we have full access to the state of the world. First, we can wear X-ray goggles and label occluders whenever they conceal all the pixels belonging to our target instance, as judged from the camera viewpoint. Second, we assign containment whenever the target is spatially inside a container, as measured by the relationships of the 3D bounding boxes. The training set is called Kubrick random because it spawns a number of random objects into cluttered scenes and lets them fall and interact in complicated ways, often giving rise to many collisions and a variety of motion patterns, but also multiple occlusion and containment events. Next, our synthetic benchmark, Kubrick containers, involves a more scripted set of actions, where we can measure the model's accuracy when the object is mostly invisible, but at the same time also being carried by a moving container sliding across the ground. The highlight of our paper, however, is Rubric, a diverse real-world benchmark consisting of videos captured essentially in the wild. We compile videos from Davis, UWS, DeepMind perception tests, and even our own recordings in the lab space. We manually label the masks at key moments such that we can evaluate under different settings to what degree the model has learned object permanence. Here are some more results. In this video, a total occlusion occurs when the bear walks behind the tree and then re-emerges on the other side. In the middle, TCOW correctly marks the tree as an occluder, and the red border corresponds to the ground truth mask. In the next example, a small package falls into pots that is then pushed to the right by a heavy box. In this case, you can see that the target object itself is not localized very accurately in the second half of the video, but we argue that is actually a good thing because you simply cannot know what the exact movement of the package looks like once it is inside, so its behavior will presumably become kind of chaotic. On the other hand, the segmentation quality for the surrounding container is nearly pixel perfect, which validates our task design choices for learning from the right signal, as well as at the right level of abstraction. Now, although the previous clip was simulated, this one is from the real world again, which implies that we are asking TCOW to process out-of-distribution scenes consisting of novel arrangements, complex dynamics, and unfamiliar visual features. Still, during the brief moment when the closer skater is positioned in between the camera and the skater we are tracking, the network again successfully predicts an occlusion. Videos where multiple identical cups are being placed upside down and shuffled around are among the most challenging scenarios out there. As shown here, we seem to be beginning to tackle them, which is an exciting prospect. Note how there is actually a recursive occlusion in the middle of this video, because the metal cup moving from right to left is briefly in front of the cup that actually contains the pen cap. For situations where there are a large number of similar-looking instances, such as these geese, again, very out of the domain, the one we are tracking in the middle is mostly kept track of, apart from the kind of apparent blending with another goose at the end. However, these success cases do not paint a complete picture, and I believe the takeaway should be that object permanence still remains far from solved. For example, this result seems to be mixed because TCOW kind of switches back and forth between the two containers and remains indecisive about what the occlusion mask should be. One reason for the confusion might be because of the semi-transparent objects that do not exist in the simulated training set. Finally, this video shows nested containment because we are placing a ball inside a mug and subsequently moving the mug into the box. The output via model starts being completely wrong at some point in the video, and in general, compositional object permanence tends to be very tricky for the model to understand. To conclude, data and ambiguity are two big challenges in this context. So we contribute a set of demanding benchmarks covering many different types of containment and occlusion. We believe that it is in the interest of applications in robotics, augmented reality, self-driving cars, smart cities, assistive technology, and so on, that future video representation and tracking models should address these scenarios more effectively. By releasing all data, code, and models, we hope to invite and encourage the community to continue working on this problem. Feel free to visit our webpage to view all these resources, as well as more visualizations of the results. Thank you for your attention.